Bolted connections are used in a variety of applications and are the most common form of steel connections used on site due to the simplicity of their installation. They are used to either connect members to other members or to connect members to various connecting parts like lugs or connecting plates. In this video, we will discuss how bolts can fail due to shearing and how to calculate the bolt shearing strength. We are also going to discuss pretensioned bolts and how the stresses in the contacting surfaces as well as the bolts change with increased pretension or externally applied loads. We are also going to discuss the slip critical and bearing type connections and how to evaluate their strength. The strength of a bolt in shear is calculated by the following equation, where if we look at the cross-section of the bolt, A sub B is the nominal area of the bolt in the unthreaded portion and F sub NV is the nominal shear strength of the bolt. The nominal shearing strength depends on the type of bolt material. Structural bolts are available in two general categories: common bolts, also known as unfinished bolts, and high-strength bolts. Only high-strength bolts can be tightened to produce a predictable tension in the bolt which can be relied on to produce a calculable clamping force. A490 bolts have a higher ultimate tensile strength than A325 bolts and are assigned a higher nominal strength. They were introduced long after A325 bolts had been in general use, primarily for use with high-strength steels. AISC specification J3.1 shows these high-strength bolts in three groups organized by strength as follows. Group C bolts are very high-strength bolts and have special environmental requirements and very rarely used in steel structures, so we will discuss only Group A and Group B in this video. The usual selection process is to determine the number of Group A bolts needed in a connection, and if too many are required, use Group B bolts. The nominal shear strength, FNV, is based on the ultimate tensile stress of the bolt with several modification factors. First, the ultimate shear stress is taken as 0.625 times the ultimate tensile stress. Next, there is a length factor of 0.9 for connections no longer than 38 inches. For longer connections, this factor is reduced to 0.75. If the threads are in the plane of shear, the reduction of the bolt area is accounted for by using 80% of the nominal bolt area. If not, no reduction is applied. The nominal shear strength of ASTM A307 bolts is based on the assumption that the threads will always be in the plane of shear. The shear strength of A307, Group A and Group B bolts rounded to the nearest KSI are summarized in AISC Table J3.2. AISC Table J3.2 refers to threads in a plane of shear as not excluded from shear planes, and refers to threads not in a plane of shear as excluded from shear planes. The first category, threads included in the shear plane, is sometimes referred to as connection type N. The designation X can be used to indicate that threads are excluded from the plane of shear, as done in the AISC Construction Manual, Table 7-1. Although it is sometimes possible to determine in advance whether bolt threads will be in the plane of shear, it may depend on such things as which side of the connection the bolt is installed from. When it is not known whether the threads are in the plane of shear, assume that they are and use the lower shear strength. For LRFD, the resistance factor is 0.75 and the design strength is equal to 0.75 times the nominal shear strength multiplied by the area of the bolt. In certain cases, high-strength bolts are installed to such a degree of tightness that they are subjected to extremely large tensile forces. A complete list of minimum tension values for those connections in which a minimum tension is required is given in AISC Table J3.1, Minimum Bolt Pretension. Each value is equal to 70% of the minimum tensile strength of the bolt. The purpose of such a large tensile force is to achieve the clamping force. Such bolts are said to be fully tensioned. As a nut is turned and advanced along the threads of a bolt, the connected parts undergo compression and the bolt elongates. The free body diagrams in the figure show that the total compressive force acting on the connected part is numerically equal to the tension in the bolt. If an external load P is applied, a friction force will develop between the connected parts. The maximum possible value of this force is F, is equal to mu times N, where mu is the coefficient of static friction between the connected parts, and N is the normal compressive force acting on the inner surfaces. The value of mu will depend on the surface condition of the steel, for example, whether it is painted or whether rust is present. Thus, each bolt in the connection is capable of resisting a load of P is equal to F, even if the bolt shank does not bear on the connected part. As long as the frictional force is not exceeded, there is no bearing or shear. If P is greater than F and slippage occurs, shear and bearing will then exist and will affect the capacity of the connection. How is the high tension accurately achieved? There are currently 4 authorized procedures for the installation of high-strength bolts. The first is turn of the nut method. This procedure is based on the load deformation characteristics of the fastener and the connected parts. One full turn of a nut corresponds to a fixed length of travel along the bolt threads, which can be correlated to the elongation of the bolt. The stress-strain relationship for the bolt material can then be used to compute the tension in the bolt. For any size and type of bolt, therefore, the number of turns of the nut required to produce a given tensile force can be computed. Table 8.1 in the high-strength bolt specification gives the required nut rotation for various bolt sizes in terms of the ratio of length to diameter. The specified rotation is from a snug position, with snug being defined as the tightness necessary to bring all elements of the connection into firm contact. In spite of all the uncertainties and variables involved, the turn of the nut method has proved to be reliable and surprisingly accurate. The second method is calibrated wrench tightening. Torque wrenches are used for this purpose. The torque required to attain a specified tension in a bolt of a given size and grade is determined by tightening this bolt in a tension indicating device. This calibration must be done daily during construction for bolts of each size and grade. The third method is to use twist-off type bolts. These are specifically designed bolts that must be installed with specially designed power wrenches. The bolts have splined ends over which an inner socket of the wrench fits. As the outer socket tightens the nut, the inner socket turns the splined end of the bolt in the opposite direction. The wrenches are calibrated for the size and strength of the bolt, and when the required tension is reached, the end twists off. This makes inspection of the installation particularly easy. In the Group A category, the ASTM designation is F1852, which has the same strength as A325. In the Group B category, the designation is F2280, which has the same strength as A490. The last method is the use of direct tension indicators. The most common of these devices is a washer with protrusions on its surface. When the bolt is tightened, the protrusions are compressed in proportion to the tension in the bolt. A prescribed amount of deformation can be established for any bolt, and when that amount has been achieved, the bolt will have the proper tension. The deformation can be determined by measuring the gap between the nut or bolt head and the undeformed part of the washer surface. Inspection of the bolt installation is also simplified when this type of direct tension indicator is used, as only a feeler gauge is required. Not all high-strength bolts need to be tightened to the fully tensioned condition. Snug tight installation is allowed for bearing type connection, where the bolt shank is allowed to press against the connected parts. Snug tight installation is also allowed for tension or combined tension and shear applications, unless the connection is subjected to cyclic loading and fatigue is a concern. Then pretension bolts are required. Pretension bolts are also required in dynamic applications or in the presence of vibrations where bolt loosening is a consideration. Pretension bolts are also required when connecting components of built-up members. A connection with high-strength bolts is classified as either a slip-critical connection or a bearing-type connection. A slip-critical connection is one in which no slippage is permitted. That is, the friction force must not be exceeded. In a bearing-type connection, slip is acceptable and shear and bearing actually occur. In some type of structures, notably bridges, the load on connections can undergo many cycles of reversal. In such cases, fatigue of the fasteners can become critical if the connection is allowed to slip with each reversal, and a slip-critical connection is advisable. In most structures, however, slip is perfectly acceptable and a bearing-type connection is adequate. A307 bolts are used only in bearing-type connections. Proper installation and achievement of the prescribed initial tension is necessary for slip-critical connections. In bearing-type connections, the only practical requirement for the installation of the bolt is that they be tensioned enough so that the surfaces of contact in the connection firmly bear on one another. This installation produces the snug tight condition referred to earlier in the discussion of the turn of the nut method. As discussed earlier, the resistance to slip will be a function of the coefficient of static friction and the normal force between the connected parts. The slip resistance is equal to the slip coefficient mu multiplied by the ratio of mean actual pretension to specified minimum pretension multiplied by the filler factor times the minimum bolt tension obtained from table J3.1 in the AISC specifications multiplied by the number of shear planes. The filler factor is equal to 1 when there is one filler layer and equal to 0.85 when there is more than one filler layer between the connecting elements. Although slip-critical connections are designed to not slip, if slip does occur because of an overload, the bolts must be capable of resisting shear and bearing. Mu is equal to 0.3 for Class A surfaces, which are steel surfaces with clean mill scale, and 0.5 for Class B surfaces, which are blast cleaned steel surfaces. The strength reduction factor phi is equal to 1 when using standard holes or short slotted holes with the slot perpendicular to the load, 0.85 when using oversized and short slotted holes with the slot parallel to the load, and 0.7 for long slotted holes. Manual Table 7-1 has the shear strength of Group A, B, and A307 bolts for different bolt sizes with the threads included or excluded from the shear plane. Also, the loading condition is taken into account, whether the bolts are under single or double shear. Manual Table 7-2 has the tensile strength of Group A, B, and A307 bolts for different bolt sizes. Manual Table 7-3 has the slip capacity of Group A and Group B bolts in Class A surfaces for different bolt sizes in different hole types under single or double shear. It is also possible to use these values for Class B surfaces by multiplying by the factor 1.67 as indicated at the bottom of the tables. Manual Tables 7-4 has the bearing strength based on the bolt distance S in units of kips per thickness of the connecting parts. The connected parts have different bearing strength depending on their ultimate strength. The table has values for 58 ksi and for 65 ksi. Other factors that influence the bearing strength are the size of the bolts and the distance between them, as well as the type of hole used. The table also includes the minimum distance between bolts required to achieve full bearing at the bottom of the table for different bolt sizes and hole types. The table also includes the absolute minimum bolt distance requirement for different bolt sizes, as well as the full bearing strength in case the bolt distance is large enough. Manual Table 7-5 has the bearing strength based on edge distance L sub e in units of kips per inch thickness of the connecting parts. Again, the table has values for 58 ksi and 65 ksi. Other factors that influence the bearing strength are the size of the bolts and the edge distance L sub e, as well as the type of hole used. The table also includes the minimum edge distance required to achieve full bearing strength for different bolt sizes and hole types. Don't forget to like and subscribe and turn on the notification bell. Thank you for watching.